In the previous lectures, we've looked at the sources of noise, we've looked at how we calculate noise and the impact of noise on circuits. In this final lecture for electronic system design, we are going to look at how to design low noise amplifiers and how to perform the analysis of those amplifier designs to confirm that the noise specification is what you decided it to be. So let's take our standard noise model here. We have on the left hand side a source sensor, and we have our noisy amplifier model here represented by a noiseless amplifier, a noise current connected across the terminals, and also a noise voltage source in series with one of the inputs. And we also have an input impedance associated with the noisy amplifier model. For the example we're going to look at here, we're going to assume the RS has a source resistance of 10 k ohms, that the temperature is 300 degrees Kelvin or approximately 27 degrees centigrade, that the noise voltage associated with the amplifier is 15 nanovolts per root hertz, and the noise current is 1 picoamp per root hertz. And we're going to consider the noise across a bandwidth of 20 kilohertz, which happens to be approximately the audio bandwidth. What we want to know is what is the equivalent input noise voltage for this circuit and the circumstances here. So first, let's write down the parameters, which is the source resistance, the temperature, a calculation here of the Thevenin input noise, and this gives the equivalent Thevenin noise for a 10 k ohm resistor. We want to work out all the noise sources, so it's the total input noise is the Thevenin noise due to the impedance of the source resistor, Vn, which is the noise voltage from the amplifier itself, and then we have this term here, which is the noise current, generating a noise voltage across RS. Plugging in these numbers, we land up with 12.9 nanovolts per root hertz, which we calculated up here. We have 15 nanovolts per root hertz from the amplifier specification, and we have 1 picoamp per root hertz multiplied by 10 k ohms, and we take the square of those to get the effective voltage squared due to the noise current flowing into the source resistance. And that gives us a total figure for our circuit here of 22.2 nanovolts per root hertz. In order to calculate out what the total noise is and the total VNI, we multiply the noise spectral density, i.e. the value per root hertz, by the square root of the bandwidth, and that gives us a total equivalent noise input of 3.13 microvolts. How much worse is 3.13 microvolts compared with the thermal noise? Well, we've got all the figures now and we can do this analysis. First of all, you'll recall that the noise figure of an amplifier is the ratio of the equivalent input noise power from the amplifier compared with the thermal noise just off the source, and we usually express it in decibels. Remember that a perfect amplifier will add no noise to the signal whatsoever, so the best noise figure you can possibly attain from any amplifier and any circuit is a noise figure of 1. But given that all amplifiers will add noise, the noise figure is always positive in dB, i.e. is always greater, and our equation for noise figure is 20 log the VNI, which is the total value of input referred noises, divided by the source noise, or the V Thevenin. And in the example here, we have our total noise is 22.2 nanovolts per root hertz. Our noise from our source, or our 10 k resistor, is 12.9 nanovolts per root hertz, which gives us a figure here of 4.7 decibels. We've now looked at the basics for how we do low noise design, Let's take another example. And in this example, we've got a source sensor with a resistance of 200 ohms, and we've got a TL071 low-cost operational amplifier configured as a non-inverting gain of ×10 by using a 9K resistor and a 1K resistor. Let's look at how we do the noise analysis for this circuit. Revising how we do low noise design and how we approach low noise design. First thing, we analyze the circuit. Secondly, we identify the main sources of noise that are occurring inside that circuit. And thirdly, we try to reduce the main sources of noise to design a better amplifier circuit for the application. Let's look at the basic parameters for the design. So we have a TL071. From the datasheet, we have a 18 nanovolts per root hertz noise voltage, and it has an input noise current of 10 femtoamps per root hertz. And because of the configuration we've designed here, our input noise current density will flow into both inputs. The first thing we need to do is derive a noisy amplifier model equivalent circuit so we can do our analysis. So here we have it. We have calculated out our Thevenin voltage here, which is 4kT times 200 ohms, and that's due to the noise equivalent of the source resistance. We have 18 nanovolts per root hertz, which is coming from the datasheet here, and we have two noise currents, one connected to either input, which of 10 femtoamps per root hertz, and finally we have an equivalent noise generator here in series with the non-inverting input node, which is equivalent to the 9K and 1K resistor in parallel because of superposition theorem. In most applications, you will be given the source resistance, and you normally cannot change that. It's defined by the sensor or by the customer, but you can modify and influence and change the design of the amplifier circuit over here. So this part here you can actually optimize for the application, but you normally cannot change the input side. First of all, let's look at the feedback network and do analysis on this. And we're going to look at the inverting input first. So here we have a noise voltage source, which is in series with the resistance of 9K ohms in parallel with 1K ohm. So we have worked out a noise voltage equivalent of 4kT times 900 ohms. We also have a noise current flowing into the inverting amplifier. And first of all, what we want to try and do is work out the total effective noise appearing at the inverting amplifier input. That will equal the Johnson or the thermal noise from the resistors plus the noise current flowing into the feedback impedance. So calculating that out, we have this term here, which is dependent on the noise current flowing into the 900 ohm parallel resistance, and we have here the thermal noise, the Johnson noise, attributed to the 900 ohm resistor. And working that through the equations, we can find out that when we do the noise current effect, this part of the equation here is so small we could ignore it. What we're really interested in is noise is dominated by the feedback resistor, which is equal to 3.86 nanovolts per root hertz. Based on conventional op-amp theory, we know that whatever happens at the inverting input will, through the virtual earth principle, appear at the other input, so we can effectively take the noise source from the negative input and place it in series with the other inputs for the non-inverting amplifier. And we still have a noise current here that's flowing into the non-inverting amplifier input. Calculating out the effect of both of these noises, because they are uncorrelated, they are both random numbers, we have to take the square of them, and the square of the 18 nanovolts per root hertz from the amplifier and the 3.86 nanovolts per root hertz attributed to the noise appearing at the inverting input of the amplifier gives us a total of 18.4 nanovolts per root hertz. So we have a lumped component at the input equivalent of 18.4 nanovolts per root hertz, which we've transferred across onto this side here. We can work out the Thevenin resistance here, which is due to the 200 ohm source resistance, and that gives us a 1.82 nanovolts per root hertz. So now we can work out the total input noise due to all the various noise sources. So we have the Thevenin noise, we have Vn from the amplifier, and we also have the In times the Rs, which is the flow of the noise voltage here flowing into the 200 ohm source resistance here. And that gives us a total figure of 18.5 nanovolts per root hertz. And I've highlighted on the equation here where the different contributions come in and how they add together to give us a total value of 18.5 nanovolts per root hertz. We've now done our first cut analysis of our circuit. We've discovered that it gives an 18.5 nanovolt per root hertz noise figure. In the next lecture, we'll look at can we improve this figure and design the circuit in a more optimum fashion to meet the requirements of the application. Thank you very much.